All right, so looking at our things on the announcements, I'm just going to keep talking. Looking at our things at the reminders board, where you have Mastering due tonight, which is Chapter 7. We'll do a group quiz on Friday. I have your individual quizzes to get back to you today. So if you want it, hang out for a minute and I'll pass them back. I update your grades the best I can on Mastering. So when you look at Mastering, you'll be able to see your grade book and you'll see quizzes, the homework grade, and as I get exam grades and whatnot, I'll plug it all in there. And it automatically does by the percentages of the syllabus, so it should give you a pretty good idea of where you're actually at in the class. I don't use Viking Web for grade book because it's the worst. I hate it, and I can't make it do what I want, so I just use Mastering. So if you're looking on Viking Web and looking at your grade, and you're like, man, I had like a 0. It's because I haven't put any grades in there, so don't look there. Plus, there's this attendance thing. You can't make Viking Web not count attendance, even though I don't count attendance. I could talk forever about how much I dislike Viking Web, but. So, first thing I figured would warm up by watching a video. Does that sound good? Okay. So last time we finished with this problem, but we had talked about the photoelectric effect and Einstein's contribution to determining the fact that light energy comes as photons and light has energy. So, let's see if I can get out of this. Sounds right.
How can Einstein be connected with the garage door opener? I'm Ronald Mallet. I'm professor of physics at the University of Connecticut and author of Time Traveler. Einstein's basic theory behind that is called the photoelectric effect. It was found in experiments that when light was shined on metal, it caused electrons to be ejected. However, what was felt was that if you increase the brightness of the light, that should increase the energy of the electrons that are being ejected. Wrong. What he found was that the electrons did not come out with more energy. What Einstein found is that it is not the brightness of the light that is affecting the energy of the electrons. It is actually the color of the light. The color is related to the frequency of light. That is to say, blue light has a higher frequency than red light. And what Einstein was able to explain was that if you shine blue light on a metal surface, you will get more energetic electrons being ejected than if you shine red light. This explanation of how the energy of the photons is given up as it kicks out the electrons and gives them their energy is the photoelectric effect. Photo for the photon, electric for the electron coming out. The other day, my friend was coming through his garage, and the garage door was coming down. Mercifully, the door stopped and went back up. How did that happen? That was based on Einstein's photoelectric effect. Because what happened was that at the base of the garage, from one end of the door, there was an emitter that was emitting a light beam across to a receiver. And in that receiver, that light beam was generating an electric current. When my friend broke the light beam, it caused that electric current to stop. And a mechanism was triggered which caused the motor in the door to cause the door to come up. So without Einstein's explanation of the photoelectric effect, we would not have the safety mechanism in garage door openers that prevent the garage door from crashing down on us.
There's your fun fact of the day, right? Same thing works for like when you're at a supermarket, right, and the doors magically open in front of you. It's the same thing. It's a beam coming down to the sidewalk, and when you break that beam, it tells the door, someone's in front of it, open up the doors. Which is why you'll see, like on sunny days, sometimes the door doesn't recognize you just because it's not getting a good reflection back up to it. So, how does that apply to the rest of chemistry? It affects us in that it helps us determine how atoms behave and how do we know where the electrons are around the atom. So this dual nature of light between the photoelectric effect and the wave nature, so it's a particle-wave combination, helps scientists think about how does it do both of those. And we developed this area of chemistry called atomic spectroscopy, really it's physics, area of physics, called atomic spectroscopy. Where it was shown that each element has a unique emission spectrum. All right, so if I'm emitting something, am I taking something in or giving it off? Right, you're giving it off. So it means that each element has, and spectrum refers to light. Each element has a unique light pattern that it gives off. So when an atom absorbs energy, it emits the energy. So right, it's going to take it in, and it can't hold on to it. It's going to give it back off. It's going to emit the energy back as light. The light that an element emits is always the same. And can be used to identify the element. And this light that an element emits is not a continuous amount of light, it's individual wavelengths. So the light emitted by an element are at specific wavelengths. So if you listen to much news about space, I don't know if anybody's a space aficionado, right? They'll tell you that, oh, we discovered this new star and it looks like it's made of hydrogen, neon, and beryllium, right? And you're like, how the heck do they know that? Because they can't travel to the star. What they're doing is they're looking at the light given off by the star, and knowing that certain elements give off certain wavelengths of light, they can pull it apart and be like, oh, it's giving off this wavelength, there must be hydrogen in there. It's giving off this wavelength, there must also be beryllium in there. Oh, it must also have some silicon in there. So by looking at the light emitted by these really far away stars and planets, we can get an idea of what they're made out of. Again, this would be more impressive in color. So look at it in your textbook. It's a much better photo in your textbook. But if I had a hydrogen lamp, so I have this tube of hydrogen gas that I excite so it gives off some light, or I put energy in it so then it's emitting light back out. I can use a prism, which you guys have probably done this, right? You have prisms when you're a little kid and you can kind of twist them around and like rainbow patterns come out. Okay, if you haven't done that, go find a prism or someone's little piece of jewelry or something, right? So the light bounces in and bounces back out as a rainbow. That's because you're bouncing off all light. If I was just using a prism to look at hydrogen light, I would just see hydrogen, 3 lines. I'd see 3 distinct lines. If I was using helium instead of hydrogen, I would see 1, 2, 3, 6 different lines. If I'm looking at barium, I see that looks like about 20 lines, right? And so where the lines are tells me which element it is. How does that make a difference about how we think about atoms? So if it has distinct lines, it must mean that our model of the atom must have distinct amounts of energy it can take in and give back off. So the idea that each element has a discrete line required scientists and physicists, especially like Niels Bohr, to think about a new model of the atom, right? So the plum pudding model already out. Now they're thinking, okay, definitely there's a center nucleus and then there's electrons around it, somehow. But if there's only certain amounts of energy allowed to be given off, well, then there only can be certain spots the electrons can be at. So in the Bohr model, electrons travel around the nucleus in circular orbits. They can only exist at specific fixed distances from the nucleus. If it's only at specific fixed distances, we call that the energy is quantized. It has a certain amount it has in it. So the energy of each orbit is then quantized, has a specific known amount of energy. And only when an electron absorbs or emits energy can it change orbits. Okay, electrons can only be in an orbit. They can't be between orbits, right? You'll never find an electron in between an orbit. It has to be in a specific orbit. And only when an electron absorbs, which means takes in energy, it can change orbits, or if it gives off energy, it can change orbits. All right, so let's take a look at my figure over here. See if I can do both of these. That's pretty good. All right, so here I have my atom. Right here is my nucleus. And here I have orbit number 1, orbit number 2, orbit number 3, orbit number 4, orbit number 5. Right? 5 orbits where electrons can be found. I have an electron in orbit number 3, an electron in orbit number 4, and an electron in orbit number 5. All of which, if they are going from a high number to a low number, they are emitting energy. They're giving energy away. So an electron travels from high energy orbit to low. That means it has to emit energy. And when it emits energy, it's going to emit energy in the form of light. So here I have an electron going from 5 down to 2. Right, that's the biggest transition we're looking at, right? 5 to 2 versus 4 to 2 versus 3 to 2. That's the biggest jump, 5 down to 2. So that being the farthest jump means it must release the most energy. If it releases the most energy, it will be the smallest wavelength, right? Because we had those were inversely related. So if I release the most energy, it means I'm at the shortest wavelength. Which you can see on my little scale here is true, right? It's at 434 nanometers. Most energy, shortest wavelength. If I look at this electron over here that's going from 3 down to 2, that's the least amount of energy. I'm only going 1 orbit difference. So if it's the least energy, then it's the highest wavelength. How do I feel about that? So far, makes some intuitive sense? Yeah.
So the further away that it is from the nucleus, the more energy?
Yes.
it has. Okay.
Yep, yep. So the farther away, more energy it has. Other questions, clarifications? All right. So that's great. Oh, question. Yeah. No.
The shorter wavelength and the highest wavelength.
Mm-hmm.
Could you maybe describe that in different terms sometimes?
Sure. I can just. How do you feel about math?
Well, maybe not math. Like.
Oh, okay.
Like when you say, because I think of shorter as like the distance is shorter. So by highest you mean longer.
Sure. You could use the word longer,
Okay.
but I'm thinking highest number. Right.
The distance between them.
Yep.
The two. Okay.
Yep. That would work too.
I was thinking like the frequency.
Yeah. No, the other one.
Okay.
Wavelength. Yep. Yeah. So how far apart 2 peaks are from each other
Okay.
in terms of physical distance, right? So this has 400 spaces between them. This one has 650 spaces between them. No problem. All right, so that is great if we're thinking about light as a particle, right? Because that makes sense. I have a particle with high energy, becomes a particle with low energy, gives off light. Oh, that's only half the story, right? Because now we have to worry about light acting as a wave. So this is where it gets a little squirrelier, conceptually. So the wave nature of an electron is the inherent property of an individual electron, which means an electron has the ability to be a wave and a particle, and each electron has its own ability to be a wave. So they're not dependent on each other. So in order to describe an electron's wave properties, we need to determine the de Broglie wavelength, uncertainty principle, and the indeterminacy of an electron. So if it's a particle, we can just use like what we know about particles to think about physics. But when we talk about electrons as a wave, we need to have a whole new set of discussion topics because it's weird to talk about a physical object, which is an electron, it has mass, moving in a wave. So we're going to have some new things to talk about. I'm talking about a an electron with mass and size actually going like this. So the first thing we're going to talk about is the de Broglie wavelength. So an electron traveling through space, right, has a wave nature. Therefore, its wavelength is related to its kinetic energy. All right, so if it's traveling through space, it must have some sort of energy because it's traveling. All right, if it had potential energy, it would be stopped. That has kinetic energy. It's in motion. And so if it's in motion and it has a wavelength, we have to be able to mathematically relate those two. So we mathematically relate them through this equation, bless you. Wavelength, all right, we've had this guy before, wavelength. Let me go ahead and box this because it is a good equation too. All right, so we have over here, lambda is wavelength. H is our same Planck's constant we had before. Now we have these two new things. We have mass, and V is velocity. So wavelength is related to the mass and velocity of the object that's traveling through space. So let's go ahead and take a break and find your calculator, and then we'll do some practice. All right, so we have a new, you'll find this is the pattern. I introduce a new equation, then you practice using the equation. That way you hopefully feel more confident about using the equation later. All right, so let's calculate the wavelength in nanometers of an electron with a speed of 4.57 times 10 to the 6 meters per second. An electron has a mass of 9.11 times 10 to the negative 4th kilograms. We have velocity. Oh, Somerset. Oh, I guess Planck's constant. We'll need that too. All right, so let's go ahead and set up our equation, plug in the things we know, and we'll see where we're at when we do that. All right, so I'm looking for wavelength. On top, I want to use Planck's constant. On the bottom, I need to use mass. And then it gave me a velocity. All right, what are some units I can cancel out right now? Because I want to be in nanometers at the end. What's something I can cancel? Right, the seconds can cancel. Is there anything else I can cancel right now? No. Okay, let's go ahead and mathematically calculate it out, and then we'll see how to fix those crazy, crazy units. All right, so I got 6.626. How many significant figures do I get in my final answer? 3, right? Because I had 4 on top, 3, and 3. I'm going to use all the same rules of multiplication and division, so I get 3 total. So 1.59. I'm in joules. Oh, sorry, ignore that. 1.59 times 10 to the negative 10th joules per kilogram meters. How do you feel about that? Is that the right units? No, super weird. Lucky for you, a joule is also, write this up here, 1 joule is equal to a kilogram meter squared per second squared. I think that's right. That. Yep. Let's do that. So I'm really going to write this as 1.59 times 10 to the negative 10th kilogram meter squared per second squared times seconds over kilogram meters per second. So now all these seconds go away. The kilograms go away. Well, oh, yeah, questions.
Where did that second come from?
I just rewrote, instead of canceling them, I just left them here to be more obvious about how they cancel out later. You could have canceled them here, and the second square would have canceled out anyway.
Oh.
Yeah. Would have worked either way. All right. And then one of these meters cancels with one of those meters. All right, is that my final answer? No, what's wrong with my final answer? I want to be in nanometers. So how do I convert from meters to nanometers? How many nanometers are in 1 meter? All right, to the 9th, 1 times 10 to the 9th nanometers per 1 meter. Or I could do 1.59 times 10 to the negative first nanometers. That would be fine too. All right, so again, this problem's not tricky. It's just plugging it in and making sure you do the right unit conversions to get to whatever they want the final answer in. How do I feel about that? Good? Good? There's some perplexed looks. All right. In that case, let me perplex you some more. Let me make this a little more confusing. Because you guys are not looking confused enough. Let's talk about uncertainty principle. All right, so we saw this a little bit earlier when we looked at diffraction patterns, right? So if an electron's behaving like a wave, it all of a sudden makes this diffraction pattern, which only makes sense if it's a wave. It doesn't make sense if it's a particle. And so experiments have shown that you can never see the interference pattern, or right, the diffraction pattern, and simultaneously determine which hole the electron went through to find it. Let's watch a little video. Maybe this will make a little more sense.
We will take an example to understand
Use German,
uncertainty
sorry.
principle. Let there be a blindfolded person in a room searching for a ball whose velocity he has been told but not the position. He will come to know the position of the ball when the ball collides with him. But at this point of time, the velocity of the ball would have changed due to the collision. This is precisely what Heisenberg stated, that exact velocity and exact position cannot be determined simultaneously.
Sound very official, right? Coming from a German person talking about a German principle. So that is the uncertainty principle. You can't know where something is and how fast it's moving on the electron scale. We either know how fast it is or we know where it is. You can't know both. So do I have this on? No. Okay. So the uncertainty principle states the following. Let's see, what's the best way to phrase this? The more accurately you know the position of an electron, the less accurately you know the velocity. Or vice versa. The more accurately you know the velocity, the less accurately you know the position. And it's because we can only envision the electron acting like a wave, in which case we know the position, or we think about it as a particle, in which case we know the velocity, but we can't really think about it being a wave and a particle at the same time. You have to choose one or the other. It's either going to be acting like a particle, or we're going to be thinking about it as a wave. Can't think about both at the same time. So if that wasn't confusing enough, let me throw one more confusing fact about electrons at you. Let's talk about indeterminacy, which is a great word. This is again what makes an electron different than a baseball, right? Something on the big scale. So macroscopic objects, things you can see, have their velocity and position known. That's called determined, right? Because if you are watching a tennis match, you can see how fast the tennis ball is moving and where it's going to land. Otherwise, you won't be able to play tennis. If you can't do that, like myself, you shouldn't play tennis because you see it coming at you and then you can't figure out where to put your hand to get it back to the other person. Don't play tennis with me, unless you want to win, in which case you can totally play tennis. Electrons, however, we don't know their velocity and position at the same time, based on the uncertainty principle. But, based on the fact we know probabilities, we can make a good guess as to where the electron can be found. So based on probability, that's not spelled right, probability. I'm missing an I. We'll just put an I in here with it. Probability. All the letters are in there, there's not in the right order. Based on probability, we can know where, in general, to look for an electron. So if I'm looking at, right, this is my tennis ball, I hit the tennis ball, I know for sure where it's going to land. If I hit an electron, I know in general it's going to follow the same trajectory as the tennis ball. It's going to be like this. And in general, it's not likely to go backwards, right? There's very few probability things that says if I hit it forward, it would actually come backwards. The majority of the probability says it's going to go this way. Right, and most of the probability is the fact that it's going to follow a traditional curve, but there's the chance it could go higher or lower than expected. But in general, I can make a really good guess as to where to look for this electron in terms of this general space. It's going to mostly, right, go that way. So indeterminacy says that we can make a good guess as to where to look for an electron. So uncertainty says we don't know exactly, but indeterminacy says we can make a pretty good guess as where we can look for an electron and how fast it's most likely moving. So have I confused everybody yet? Yeah. Oh, can I turn on the lights? Yeah. Oh, the heat? I'll check back up to neutral. There we go. All right, so now we have in our knowledge notebook, wherever you keep your knowledge, in your head, I guess. We now know that an electron is a wave and a particle. If it's a particle, it has certain properties. If it's a wave, it has certain properties. You can't think about it as a wave and a particle at the same time. But we have a pretty good guess of where we can find it, at what time. And if we think about it as a particle, we know what energy it has, and we can make a good guess of what kind of energy it's going to emit based on what energy level it's in, which means we can now put it all together and start describing the atom and where we can find electrons in an atom. So, many properties of an element are determined by the energy of the electrons, right? And so energy is related to velocity through the equation we did like 5 minutes ago, right? Energy and velocity are related. But it's indeterminate exactly what the velocity, or uncertain what the velocity is known its position. So how do we put all those things together? Luckily, you don't have to. A really famous physicist named Schrödinger mathematically described a way to determine where best guess an electron is and how best guess fast it's going. He was able to describe this using something called a wave function. So a wave function has the symbol psi, in case you didn't know that. That's the letter psi. You can think about it this way, like imagine you're watching The Little Mermaid, right? What was the name of the dad in The Little Mermaid? Right, it's a trident, right? Poseidon has a trident. It's psi. They all come from the same Greek. Poseidon has a trident, which is what that is. So there's your fun. There's 2 fun facts for today. Total icebreakers when you're hanging out in line at lunch. You're like, hey, have you watched Little Mermaid lately? Did you know? I think that's a goal. I try to give you 1 icebreaker per class, just so that you can make friends. That's my goal. You can use chemistry to make friends. All right, so we have this wave function psi, which is a way of describing the energy of an electron, as well as the probability of finding an electron in a given volume. If you would love to know more about this, you can take an entire class on it called physical chemistry, where they mathematically derive how they get to this. I'm going to skip to the ending and tell you that you can solve it. And once you do solve it, you will find that we describe a wave function using orbitals, like we saw when we talked about the Bohr model, right? Each spot an electron can be is an orbital, like they have orbits around the nucleus. So we can describe the wave function using orbitals that are described. All right, so we use the orbitals to describe the wave function, and we describe the orbitals using 4 quantum numbers. So to describe the orbital, we have these 4 numbers that tell you everything you need to know about the orbital, and that one orbital can then tell you about the wave function. So let's work through what those 4 numbers are, how we know what they are, and what do they mean. So let's talk about the one we've actually already looked at. So if I flip back to this picture, right? This picture had 1, 2, 3, 4, 5 listed on it. those actually n equals 1, n equals 2, 3, 4, 5. So that n is called the principal quantum number. And determine that number tells me the size and energy of the orbital, which is what we saw in that picture right here, right? So if I'm looking at n equals 1, it's the smallest orbital, has the least energy, right? N equals 2, slightly bigger, more energy. N equals 5, even bigger, even more energy. And so this n tells me about size and energy. So n can have values 1, 2, 3, 4, 5, whatever, all the way on up. It can only be whole number values though. So there's no fractions, right? Because we already said an electron can't exist in between an orbital, so it has to be a whole number. It's either at 1 or it's at 2 or it's at 3. And you can see in my fancy little, I'll call it a graph. Over here, I have energy going up and down. N equals 1 is the lowest energy. N equals 2 is higher energy. 3, 4. What's the other thing you notice about what's going on here with the spacing? Right, the higher the number, the closer they get together. So for orbitals, the larger the n value, the closer in energy they are. So that means they're also closer spaced to each other. So the picture we had before was good, but it really should look more like this. Like 1 is pretty close, 2 is kind of far away, 3 is a little closer, and then 4 is closer to it, so then 5, and it's 6. Almost touching, totally shouldn't have actually touched. Right, but the farther they get away, they're actually much, much closer in physical space, and they also have smaller energy differences. All right, so that makes sense based on the pictures we've seen. The next 3 numbers are less intuitive. So let's talk about the second number, which is the angular momentum number. And it has every number has a letter that goes with it that also refers to a number. So this is quantum number 2, and that is the angular momentum number, but its values are not 2. It'll make sense here in a second, maybe. All right, so this is an L. I tried to make it it should probably look more a little scripty. Maybe that's easier if it's an L, like a cursive L. So the angular momentum number, L, determines the shape of the orbital. It tells you, right, based on probability, what shape should I be looking in? Should I be looking in a sphere? Should I be looking in a triangle? Should I be looking in a box? What kind of shape should I be looking for this orbital? L can only have values of the following. It can have the value 0, 1, 2, 3, but it's dependent on what n you chose. All right, so if you choose n first, then L is based on whatever n you chose. It can only be up to n minus 1. So let's think about that. Let's say I pick an n equal to 2. What are my options that L could be if I choose n equal to 2? Right, 0 and 1. Why can't it be 2? Right, because I chose 2. So 2 minus 1 is 1, or 0. Okay? What if I choose n and equal to 5? What are my possible options of L values? 0. Yeah, 1, 2, 3, 4. Okay, those are all the possible choices I could have. So you got to pick your n first, and then your L is based on your n. You're thinking, oh, that seems pretty straightforward. Until L values have numbers that also are letters. So you have a number that tells you that's the second quantum number, which means L, then L has values that also are letters. Yeah, you got it. All right, so if I have a value of L that's equal to 0, that's given the letter S. We're going to do a bunch more of this on Friday. It'll come together on Friday. Feeling optimistic. If I have an L value equal to 1, that's given the letter P. If L equals 2, we call that D. If L equals 3, we call that F. There are more letters beyond that. We're just going to do these 4 letters. So you're thinking, why do I need a letter to tell me about the number, to tell me about the shape, and how it's related to n? Well, the letters refer to the physical shape they take on. So this sphere is L equals 0. What shape is that? It's a sphere. Oh, it's an S. Right? S. S tells me 0, tells me sphere. Right, so the letter tells you about the shape, and the number tells you about they should tell you all the same information. All right. These 3 options right? So I can have a dumbbell in any of the 3 directions of an axis, right? I have a dumbbell going out, dumbbell going up, a dumbbell going 90 degrees. So those 3 shapes tell me that's a L equals 1 equals P equals, I don't know, a clever word that starts with P that means dumbbell. I'm sure there must be some mathy term. I'll have to ask a math guy. Mm-hmm. Maybe it's a peanut. Maybe, yeah, that's good. We'll go peanut. All right, so if L equals 0, there's only one option. If L equals 1, there's 3 options. If L equals 2, how many options of shapes are there? 5, right? 5 different shapes I could put it in. So they're related. If I have just L equals 0, it means I only have 1 option. If I have L equals 1, I have 3 options. If I have L equals 2, I have 5 options. How is L related to N? Right? For L equals 2, what is the biggest number N could equal? 3, right? N equals possibly 3, which is a much bigger energy than this. So more energy, more ways to put that energy. So I have more shapes available to me. I don't have a picture for it, but what if I had L equals 3? How many possible shapes could I have?
7.
7 shapes, right? Because L equals 3 means that the N value could be all the way up to 4, which means I have even more energy, more space, more places to put my electrons. All right, we will pause there. We will